Hi, my name is Lukman Azad bin Arif. My matrix number CN240047. This video I would like to discuss about introduction this project. Newton law of cooling tell us how sometimes hot cool down over time. It says the bigger is difference between the object temperature and the air around it, the faster it cool. Even though it's named after Isaac Newton, he didn't write it the way we use it now. The full idea came later, where the scientists learned more about the heat and temperature. This law is useful in real life. For example, cooling drinks, cooling machine, in forensic to know how time of the that person. Another topic is spring mass system. This is why weight is tied to a spring. The moment of weight depend on string. Initial, how hard is to move. Second, spring force, the spring pull it back. And lastly, damping, the force to slow it down. We use it to study the system and find out how it moves over time. In short, both Newton's law of cooling and spring mass system help us to understand how things cool down or move. They are useful in science, machine, and daily use. That's all. Thank you.
Hey, hi, my name is Benedict Daniel. So in methodology, I will explain about method that we use in problem 1 and problem number 2. So problem 1, we use which tell us about the Newton law of coolings, and then the problem number 2 it tell us about a damped mass spring system. Okay, the method that we use to solve this problem is the first one, separable differentiation equation, homogeneous differentiation equation, and Laplace transform. Okay, in the problem 1, we use a separable equations. Why we use a separable equations? Because it involves a Newton law of cooling. Okay, when we use a separable equation method, because the cooling model can be written in the spread way in terms of variable. Okay, with that kind of spread, this is allow us to integrate both sides and find exact expressions for temperature over the time. So we think separable equation is the most perfect method we can use because it gave us a simple direct way to solve this kind of first order differentiation equation. Okay, for the second problem number 2, what we use is a homogeneous differentiation equation. Okay, for the homogeneous equations, okay, for the problem number 2, which is involve a damped spring mass system, we use homogeneous differentiation equation. Why we use the homogeneous? Because this system are no external force acting on the mass. Okay, we use the second order homogeneous differentiation equation, meaning that all the term involve function of x, and it can be derivative, and also it tells us how the system behave on its own. Okay, like how the mass vibrate or returns and rest due to the damping lah. Okay, by using homogeneous, it's help us a lot to understand the natural motion of the system. Okay, the lastly is Laplace transform. For the Laplace transform, finally, why we use Laplace transform to solve this spring system method? But in the initial condition lah, it must be initial condition. Okay, the Laplace transform is very useful in engineering because it turns differentiation equation into a algebra problem. Okay, which that Laplace, we can include this value directly in the equations. Okay, we conclude in the Laplace, this method is more faster and more systematic and ideal when come to initial conditions. That's why we use Laplace to this problem. So for the conclusion, we use a separable equation for the cooling problem because it was easy to separate and integrate. That the first one. The second one, we use homogeneous because also we can understand the spring system and the natural motion lah. And for the third one, Laplace transform, we can use or we can solve the problems with initial conditions perfectly or efficiently. So we use three methods to solve our problem, number 1 and number 2. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Asam bin Muhammad Bantrang. I will explain about the application of ODE to solve the Newton law of cooling. First of all, to solve the problem, we must consider 4 key point, which is understanding and application Newton law of cooling, parametric estimation, prediction use of the model, algebraic numeric regression. So the formula given to us is dt over dt equal to minus k multiplied by t minus m. T is the temperature of object, m is constant temperature of surrounding medium, k is positive cooling constant that depend on the object and its surrounding, dt over dt is the rate of change of absolute temperature. So first of all, we must use a separable method, which is separable left and right side. After that, we integrate the both side and to eliminate ln which must add exponent, and then the final answer is t equal to m plus ae power of minus kt which is ec equal to a because ec is constant and a is constant. And then we must find a using the initial value problem, which is we can assume that initial temperature, which is TO equal to 0. So we substitute the equation to the GE, we get initial problem equal to m plus AE 0, AE power of 0. We know that exponent 0 equal to 1 and A equal to T initial temperature minus m. We substitute back to the GE, and the final GE we get T equal to m plus TO initial temperature minus m multiplied by exponent power of negative KT. Okay, next we must find the constant K using the formula that given to us. The information given to us is the soup has been cooled from 90 degrees to 16 degrees in 10 minutes in a room temperature at 20 Celsius. So we get the initial temperature TO equal to 90 Celsius, temperature after 10 minutes T10 equal to 60, room temperature M equal to 20 time T equal to 10. Remember that our GE equation is T equal to M plus TO, T initial minus M multiplied by exponent power of minus KT. We substitute our information into our GE, and we get the K constant equal to 0.056 minutes. After that, we can solve the solution A, which is how much longer will it take the soup to cool to 35 Celsius. So the question want us to know how much longer it will take from the soup to cool for 35 Celsius. So we need to find the total time it take to cool from 90 to 35 and then subtract the initial 10 minutes. So let total T total be the time to the cool to 35. We substitute the information in our GE, we get the temperature be cool is 35 equal to 20, which is room temperature, minus 19, which is our initial temperature, minus 20, which is our room temperature, multiplied by E, negative 0.056 multiplied by T total, and we get our T total equal to 27.51 minute. And then to know addition time, we just subtract the to the 10, which is the first cooling time from the soup, and the addition time is 70.51 minute. Now we can go to the problem B, finding the cooling time in the freezer. Now the cup of 90 Celsius soup is put in the freezer whose temperature is minus 50 Celsius. We want to find how long it will take for the soup to cool from 90 to 35. We will use the same cooling constant K we found earlier. Assume it's primarily depend on the soup cup and the soup given. So we get the initial temperature TO equal to 19, final temperature T final equal to 35, and the freezer temperature M equal to minus 15. Remember our GE equation is T equal to M plus initial temperature minus M multiplied by E minus power of negative KT. Substitute all the information we get to our GE equation, and we get the T equal to 30.25 minute. So from the problem 1A, it will take approximately 70.51 minute longer from the soup to cool at 35 Celsius in the room temperature. From the problem B, it will take approximately 13.25 minutes for the soup to cool from 19 to 35 in the freezer. In conclusion, Newton's law of cooling provide the robust mathematical model to quantity how an object temperature change when they exposed to the surrounding medium of the different temperature. The rate of cooling is directly proportional to the temperature differences, and the specific properties of the object is interface with the environment of and circulated in the cooling constant K. The calculation clearly show that the cooler environment, the freezer, result a significant shorter cooling time to reach the target temperature compared to the warm environment, which is room.
Hi, Assalamualaikum. My name is Ahmad Azim Saidi, number matric CN240083. So today I'm going to talk about problem 2. So we got the equation. The equation said x double prime plus a over m x prime plus k over m x equal to ft equal over m, where mass m is a mass, a is resistance, k is a spring constant, and ft is an external force. Suppose that mass of 2 kilo is suspended from a spring with known spring constant of 4 Nm and allowed to come to the rest. The damping resistance constant equals 6. The mass is released with a downward velocity of 3 meter per second. Assume no external force, find an equation for position the spring at any time. Use a homogeneous equation and Laplace transform. So this is the our value that we get from this paragraph. As we can see, first we do a homogeneous equation. Since ft equal to 0, the equation will become x double prime plus 26 x prime plus 24 x equal to 0. So as you can see over here, we require homogeneous equation, so we get this x double prime 3 prime plus 2x equal to 0. So second, we do a Laplace transformation. Apply the Laplace transform to the homogeneous equation, which is x double prime plus 3 prime plus 2x equal to 0. Let xs equal to L, s equal sx xt, and use the standard Laplace transformation. So let's let SS equal to let SS equal to LXT and use the standard Laplace transform. As we can see over here, this is the equation. So we assume S0 equal to 0 released from the rest position and S prime 0 equal to 3. Then factor the denominator. So for factor denominator, SS equal to 3 over S plus 1 and S plus 2. So use partial fraction decomposition. So as we can see over here, we get 3 over S plus 1, S plus 2 equal to A over S plus 1 plus B over S plus 2. So this is the solution for the solving. After that, we get S equal to 3 over S plus 1 minus 3 over S plus 2. Check the inverse Laplace, so we get St equal to 3 exponent minus t minus 3 exponent minus 2t. For the final answer, homogeneous equation, we get x double prime plus 3 prime plus 2x, 3x prime and 2x equal to 0. The solution for using Laplace transformation, we get xt equal to 3 exponent t minus 3 exponent 2t. So for the interpretation of the result 2, the given problem describes a damped mass spring system where a 2 kg mass is suspended from spring with a constant of 4 Nm and damping constant of 6 with no external force acting on it. The system is released from the rest with an initial downward velocity of 3 ms. From the given parameter, the homogeneous differential equation governing the motion in x double prime plus 3 prime plus 2x equal to 0 using Laplace transform and applying initial condition x 0 minus equal to 0 and x prime 0 equal to 3. The solution obtained is xt equal to 3 exponent minus t minus 3 exponent minus 2t. This solution represents an overdamped response, meaning the mass returns to equilibrium without oscillating. The exponential terms indicate that the displacement decreases over time due to damping. And eventually, the system comes to the rest. The absence of oscillation and gradual return to equilibrium show the effectiveness of the damping is absorbing motion energy and stabilizing the system. Thank you.